Hello and welcome to Lesson 5. Before we start this lesson, what I'd like to do is to continue our exploration of how polymer processing operations make materials that are used every day worldwide. So today, I'd like to think about something that at first sight might not seem like a product from the polymer processing industry. So what could I be talking about? What I'd like to think about today is clean, fresh drinking water. And so, in the West, we take this for granted. In many parts of the world, however, clean, fresh drinking water is a scarce and precious resource, and one that has to be managed and fabricated on a daily basis, because many indigenous water sources just aren't safe to drink and cause multiple diseases, thanks to waterborne parasites. So one of the energy efficient ways that clean drinking water can be made is via a filtration or osmosis based process. And so there's microfiltration, there's ultrafiltration, there's reverse osmosis, all of which will serve varying levels of removal of waterborne nastiness. And so if one looks at a reverse osmosis membrane cartridge, or an ultrafiltration membrane cartridge, typically you see a little bit like what I have on the whiteboard there. You have a replaceable modular unit that you can put into a plant that produces clean water. The question is, what's inside this and how does it actually work? So let's take a bit of a zoom in. If we zoom into one of these modular cartridges, what you find are bundles and bundles of bundles and bundles of very, very small pieces of tubing. Okay, fine. The tubing might be, say, I don't know, 1 millimetre in internal diameter, something of that nature. And there might be a bundle of 10 or 20,000 of these potted in resin, such that the dirty water can flow on the internal sides of these and the clean water can flow on the external sides, or vice versa, depending how it's configured. The clever bit, however, comes when you zoom in onto one of these tiny polymer tubes, and that is what is in the red insert on this board at the moment. So in that red insert, I've put a scanning electron micrograph of a section of the wall of one of these tiny tubes. And what one can see here is a functional structure that allows that water filtration to take place. And so in that picture, what you can see are effectively two skins, an inner skin and an outer skin. These skins are actually nanoporous. They have tiny, 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 tiny pores that will allow water molecules to pass through them. Those tiny porous structures are supported by what looks like a foamed type structure in the core of the wall there. And if one looks carefully at the core of the wall, you'll see that this foam structure is actually graded in pore size. And those parts of the foam closest to the inner wall have a larger pore diameter, and those closest to the outer wall have a smaller pore diameter. And if we think about materials of construction, typically this can be a polymer such as polyether sulfone, the structure of which I've also put on the board there. So the question then becomes, how do we make one of these nanoporous or microporous structures in a way that is economic and cost effective and reproducible and realizable on a very, very large scale? Because if one thinks of the demand for clean water globally, it's huge. If one thinks how that translates into how many reverse osmosis or ultrafiltration membrane modules this requires, it's a very, very, very large number. And so the method by which one has to fabricate the working component of these membrane filters has to be a continuous process that can work at very, very large scale, but has to achieve incredibly small microstructure. So let's have a little bit of think about the polymer solution spinning process, because this is the way in which these membranes are made. So for once, I'm not talking about a classical melt extrusion based process. One could say this is extrusion, because it involves squeezing fluids through a die, as we'll see in a minute. But this is not done in the melt phase, it's done in solution. And so what you have are effectively two reservoirs to start with. One reservoir is a reservoir of a polymer solution, so it'll be polyether sulfone dissolved in a solvent of some sort. And then we'll have something called a bore fluid. And we'll see the function of this bore fluid in a minute. Let's think about the polymer solution to start with. What typically one needs is a solvent that dissolves the polymer, otherwise you can't make a solution, but that solvent has to have a very special property. That solvent actually has to prefer water or bore fluid in preference to the polymer. So not only does it have to dissolve a polymeric structure very, very well, which is typically going to be carbon chain based, it also has to have an affinity for polar solvents. So one of these solvents is N-methylpyrrolidone, the structure again I've put on the board there. And so what one does is one makes a pretty viscous, pretty highly viscous solution of N-methylpyrrolidone and let's say polyether sulfone. And also one has this reservoir of bore fluid, which is typically water-based. It might be water with a bit of glycerol. And then what you have are two very accurate metering pumps, typically gear pumps, that feed both of these solutions into a hollow fibre die. Now, way back we talked about fibre melt spinning and spinnerets. This is solution spinning, and this too is a spinneret. But it's a slightly different type of spinneret than what you'd see for melt spinning. So let's have a little look at that in some detail. So a hollow fibre spinneret typically consists of two flow passages. One of these flow passages is where the polymer solution comes in, and the other flow passage is where the bore fluid comes in. Now the diagram I've put on the board there showing the polymer solution inlet and the bore solution inlet is a cross section of a cylindrical structure. So the bore fluid path, which is in yellow, is effectively a pipe that goes through the centre of this die. And the polymer solution inlet is effectively an annulus which converges onto where that bore fluid is. So let's zoom into that zone of convergence. And what we see here are two exit orifices. One is effectively looking like a pipe. That's where the bore fluid comes out, right in the centre of the die. And in a thin annulus surrounding that pipe, you have the polymer solution. And so effectively what you're doing is you're co-extruding the bore fluid and the polymer solution together such that they come into good contact with one another. Okay, so when these two components come into good contact with one another, some kind of magic happens, because what you have is a solvent that has dissolved a polymer, polyether sulfone, but that solvent actually prefers being in the bore fluid. And so as soon as those two components are co-extruded and the polymer solution comes in contact with the bore fluid, the solvent migrates away from the polymer into the bore fluid. Moreover, what then happens is that the resulting viscous solution that is extruded is passed into what is known as a coagulation tank. Now, this has a makeup that is very similar to bore fluid. And so what happens when the uncured hollow fibre hits this tank is the remaining solvent that hasn't already migrated into the bore fluid sees the coagulation tanks and migrates into the coagulation bath. And so what we have is a means of precipitating a polymeric structure, because the solvent is preferentially diffusing either into the bore fluid or into the coagulation tank. Now that rate of diffusion determines the pore size. And so if the mass transfer is very, very fast, you get one pore size. If the mass transfer is very, very slow, the polymer's got more time to coagulate and form a structure, so it forms a slightly larger type of pore. So what we have is an ingenious manufacturing method here that is all about mass transfer. And it's about the mass transfer of solvent from a solution into either bore fluid or a coagulation tank, because that allows this microporous or nanoporous structure to be precipitated out. And as we saw with melt spinning, you can run these processes at quite a high rate, but the rate in this case is going to be limited by how quick these diffusion processes happen. So once the hollow fibre to be is in the precipitation tank or the coagulation tank, you have then what looks like a fairly classical set of rollers for drawing out the fibre, and then for drying, and then for spooling the fibre. So if you want to see this process in action, on the board there, and again in the description of this video, I've put a link to a laboratory scale polymer solution spinning process, which shows all these various stages in some sort of detail.